네, 알겠습니다. All right, let's begin. So today we're gonna, welcome to week six. So today we're gonna talk about generative adversarial network, GAN. So four subtopics. First, GAN, and then there are a couple of, there are several generative models or generative model philosophy, to be more specific, which are VAEs, which we talked about last week, VAE. So we can either use VAE for creating a new sample, or I'm just going to stick to image generation in this talk. So we're just going to talk about image generation. So we can either create image, like MNIST images or face images or Imagen images, whatever, with either VAE or autoregressively, or using GAN, or actually, I forgot to mention it here, there's also another model called diffusion, which is a bit more recent. Well, I mean, diffusion was proposed way back in 2015, but now it's only now catching a lot of traction these days. So there are mainly four families of generative models. And to be honest, VAE is not so popular these days. So the go-to methods these days are either, well, I would say diffusion is kind of like dominating, but there's still like some people suggesting that the autoregressive models are still a very, we're only sticking to the image generation, but autoregressive models are also doing a fine job. If we go to text generation, then it's mostly autoregressive models. So we're going to talk about that today as well. And how to evaluate a generated image, because if it's an image that we've never seen before, how are we supposed to know how good it is? So some evaluation methods, and then application of GAN. All right, so VAE recap. So VAE was just a added regularization term using KL divergence on top of autoencoder, right? So it's just autoencoder reconstruction error here, and KL divergence here to put some structure into the latent space. Specifically in VAE, we put a Gaussian distribution structure in the latent space. There was a question. 출석, 네, 오늘은 출석은 없다고 말씀드렸습니다. Right, so that was VAE, and right, this allows to learn approximate posterior. So what we want to do is we want to learn a true posterior, true distribution over Z given X, which would be the latent space in our autoencoder. But since we don't know it, we approximate it with a manageable or an easier function, which is typically a Gaussian distribution. So then we know that if we have a pretty good approximated QZ, which tries to approximate the true PZ. If we have a good enough QZ, then we can sample from QZ. We can sample as many Z's as we want from QZ, and then assume that it is a good sample. So, for example, if the true distribution of PZ, this says it's PX, but it's PZ, PX doesn't really matter. If we have a true distribution that we want to approximate, so this is the true distribution here, which have two modes, which have two modes, and since we don't know what the actual true distribution looks like, we try to estimate it, or we try to approximate it with a known distribution function Q, which is Gaussian in this case with Q. So if we have a Q that looks like this, then at least we're covering one mode. So any Z's or any X's that we sample from here and under this green support will probably be a good enough approximation for this particular true distribution here, because this is the true support. Well, actually, there's another support here. There's another support, but we're going to miss this part, but at least we're covering this part. But to be really technically correct, if we try to learn a VAE, if we try to approximate PZ given X with QZ given X using a VAE philosophy, then the true distribution, the approximated distribution, would actually be something like this. It would try to cover all modes, all support, because P support starts from here all the way to here, although there's a lot of missing parts here, but still the support is pretty wide. So using reconstruction error and KL divergence, then the Q support would try to cover the entire support like this. So there will be a lot of unlikely samples drawn from here, actually, because in reality, PZ given X, or the true distribution, has very low likelihood or very low density in this region, but since our Q has a highest mode here, then we'll be actually sampling a lot of incorrect samples, but that's the nature. All right, so another generative model family is autoregressive model. So these are pretty old works. Pixel CNN, WaveNet, these are pretty old works. They were proposed back in 2016 or 17, if I'm correct. So 5 or 6 years ago now. Pixel CNN is basically generating images 1 pixel at a time. So if we have a 128 by 128 resolution image, then you sample 1 pixel, another pixel, another pixel, another pixel, another pixel, another pixel, in order, in order. So that would take quite a long time. You need to run a for loop over 128 times 128, right? So which is what? Which is 272724. You would have a 40,000 iterations over. And WaveNet is similar idea. It generates audio 1 frame at a time. So if you think about your MP3 audio files, they usually are recorded with a sampling rate of 128K, or if you're listening for a high quality audio, you would have a 256K sampling rate, and that means that a single second of an audio consists of 128K. So 128000이죠. 128K frames. Well, not frames, but like units. So if you want to generate like 5-second audio, then it would take a lot of time using WaveNet. GPT-3 is a more recent work compared to these two. GPT-3 was proposed back in 2021, but so there was GPT-1, there's GPT-2, then there's GPT-3. So GPT-1 was proposed probably back in 2019 or something, but GPT-3 was presented in 2021, and it's generating 1 word at a time, or actually 1 subword. But we're going to get to subword encoding in the second half of this semester, so you can wait for that. But simplifying, you can when GPT-3 generates a bunch of text like sentences or poems or programming codes or whatever, like news articles, it will generate 1 word at a time. So again, if we are generating a very long text like a novel, then it would take a long time. About the same time, DALL-E 1 was proposed. I think it was in 2021, I think. And in DALL-E 1 is actually a text to image generator. So it's a conditional image generation. So it's a conditional image generation model. So you give a short description of what kind of image you want to generate, and the DALL-E 1 would generate it. And the way it generates is based on generating 1 visual code at a time. So if you're familiar with something called VQVAE, which is a short for vector quantization, VAE, vector quantization VAE, which was proposed back pretty like way back in 2018, I think, or 2018, 2019. So we're not going to talk about vector quantization in this class, but the gist of it is that you have an autoencoder. You have an autoencoder of an image. So this is a raw image. So this is some xi, and xi is an image. It's an image, and then you compress it, and then you decompress it. So there's encoding, and there's decoding. And when you have a z latent representation, and a compressed representation, for example, if your image is 128 by 128, then your resolution would be like 40K, right? And your z would be, I don't know, your z could be like maybe like 512 or something, and then the original space would be 40K again. So what you want to do in VQVA is that you want to replace the 512 dimensional z vector into a code. So normally in autoencoder, your z is a continuous distribution, your z is a continuous variable. But here in VQVA, you have a separate code book. So there's a separate code book, and your z would also be so your z, this is your z, z would be, actually I should have, right, I should have, Yeah, I shouldn't have flattened it because if you use a CNN as an encoder and decoder, then your Z would be two-dimensional actually, because your image is three-dimensional. Your image is 128 by 128 by 3, your RGB. Then your Z would be something like there's like a spatial channel. So there's a spatial channel. So this is your Z. Then this is your spatial dimension, and this is your channel dimension. So, well, we haven't even gotten to CNN yet. So this is all like talking about the future stuff here we're going to learn. But if you're already familiar with CNN, then there's channel and then there's spatial. There's a spatial dimension, then there's channel dimension, right? So in your latent variable Z would have a channel and spatial dimension. So it will be a two-dimensional structure. So this could be like your channel could be like 256 dimension, and then your spatial could be like 512, something like this. And then what you do within VQVA is that you have another word embedding like you have a lookup table. Like there's like code 1, code 3, code 4, 4, 5, 6, all the way to like maybe 1024 codes. And then you replace each of the fibers, each of the feature maps with one of the codes. So this first fiber will be replaced with code number 4, like some nth, your ith fiber would be replaced with code number I and code number 1, something like this. So you're basically discretizing your latent variable. So by doing so, you can have a visual code of any given image. So your image would be basically converted to like a sequence of codes instead of like sequence of feature maps. Then you can use that to auto-regressively generate any image you want. So if you're interested in DALL-E 1 and the VQVAE, please look up this work, VQVAE, and also there's a follow work called VQGAN, and there's VQGAN version 2 as well. And then very recently, Google has released a model named Party, which is based on VQVAE. Right. Okay, so all these models are autoregressive, meaning that when you want to estimate or when you want to sample a new X, you need to have a likelihood, and that likelihood can be broken down into a factorized form like this. So if you have a P X1, X2, this is all different dimensions. This is not different samples, like X1, X2 is all different dimensions. So for example, let's assume that you are generating a word of 256 words, for example, let's say, PX, like a sentence that consists of 256 words, then your joint distribution or joint likelihood can be just broken down into P X1 and then times P X2 given X1 times P X3 given X2 X1, all the way to P X256 given to X255, all the way to X1, something like this. So you can factorize it. So that's basically what you're doing with autoregressive model. First, you sample this, and then based on this, you sample this, based on this, you sample this, so on and so forth. So yeah, sometimes impractically slow. And the third generative model is the one that we're going to talk about today, which is GAN. So note that in VAE, you do have an approximation of PZ given X. So you have QZ given X. So you have some likelihood function that you can use to, estimate how likely your sample is. And in autoregressive model as well, you can break down your likelihood function into a factorized form, so you can still estimate the generated. You generate a sample, and then you can estimate the likelihood. You can calculate how likely was your just generated sample using VAE and autoregressive models. But what if you don't care about data distribution? What if you don't care about the likelihood? You don't care about anything. You just care about generating a good synthetic sample, and that's it. So you don't care about the likelihood, the distribution. You don't want to estimate any of that. You don't want to know the functional form of the distribution that you want to approximate. So in that case, you can use something called GAN. So here, what GAN does is that you have an input random noise. So you sample a Z from a random distribution. It could be Gaussian distribution, it could be uniform distribution, so it could be anything. It could be Gaussian, or it could be uniform, could be actually anything. So some random distribution. Then you can get a Z out of it, and then you put that Z into something called generator network. So it could be seen as a decoder. And you put the Z into generator network, and then the generator network will generate hopefully a very realistic sample, in this case image. So, and that's it. So you don't care about, so there's no approximating the distribution of the images, or trying to do a variational inference on the image, like latent distribution of the images. None of that. You just have a random noise distribution and a mapper, basically a function that maps a random noise to a real sample, and that's it. So that's what we want out of a GAN, and there would be, of course, there's a discriminator network that works as a referee to evaluate how likely your fake sample is. So we're going to get to that. So this is the gist of GAN. We don't care about the data distribution. We only care about generating good samples. But there's another new player in the scene, which is diffusion, which also doesn't care about data distribution, actually. So we're going to get to diffusion at the very late stage of this entire course. I think it's the second to the last, actually. So just speaking on the very high level, what diffusion does is it's gradually adding noise or removing noise. So here there's a very good illustration of what's happening in diffusion. So you have a true image, a real sample, real X sample, and then you start adding small amount of noise in a chain fashion. You add some noise, you add some noise, you add some noise, you add some noise, and eventually when you add enough amount of noise, then your sample would look like just complete garbage, just noise itself. So if you can do that, so this is the forward process. If you can do that, if you can inject small amount of noise, then you can probably go reverse. So you can probably take away, take away small amount of noise back to original form. So for example, if you have an image that looks like this, then you can have a pretty strong denoising function that can go to here, right? So if you have a strong enough denoising function, then you can actually start from here, denoise a little, 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 until you get a very nice looking picture like this. So that's the essence of diffusion models. So it can be seen as a multi-step VAE. So if you think about VAE, what VAE does is that you have an image, and you have a latent space, and you have a reconstructed image, right? So what VAE does is that it sends the original image in one step, sends to a Gaussian distribution, right? Gaussian distribution. And then it, in one step, decodes back into the original image. But here, you add the noise that you add in the diffusion is usually Gaussian. It's usually NOI. So what happens in diffusion is that you don't send your sample directly to the complete Gaussian distribution at one step. You actually take multiple steps, like thousands of steps, to get to the Gaussian distribution, and then come back with a lot of steps as well. So you can think of it as a multi-step VAE. So it has all the things, all the VAE friendly terms all here, like Bayes rules, variational inference, reparameterization trick. It's all there in diffusion. So when you get to diffusion, you will be very familiar with you should be familiar with all these terms. So in a educational perspective, it would have been nice to dive right into diffusion right after VAE, because there's so much similarity between the two. But diffusion is and diffusion was proposed back in 2015 by in a more physics friendly context, because diffusion has a very close connection with something called Langevin dynamics. 그러니까 랑주뱅이라는 물리학 혹시 들어보셨을지 모르겠는데, 이제 랑주뱅 역학이랑 굉장히 이제 관련이 있는데, 그래서 이제 물리학 하신 분이 2015년에 제안을 하셨고, 이제 한동안 이제 그냥 뭐 주목을 못 받다가 이제 2019, 20 들으면서 이제 막 주목을 받고 있어가지고. So in an educational perspective, it would have been nice to go right after VAE into diffusion, but since I'd like to keep this whole course in a chronological order, so that's why we started from autoencoder, which is like a very old concept, and then we're building up. So we're going to talk about diffusion right after we've talked about transformers and multimodal models, because diffusion is usually used in in conjunction with transformers to generate images these days. All right, moving on to GAN now. So GAN, so far any question? All right. Yeah, I mean, if you want to, you can study diffusion in advance because we're gonna have, if you want to wait for my lecture, you're gonna have to wait until like the end of the semester, which would be like the late November or something. Anyway, so back to GAN. So GAN is a two-person game. So there's a generator and there's a discriminator. So as I said, generator tries to generate images or samples as realistic samples as possible, and discriminator is basically a discriminator. So it's a referee to evaluate how realistic the generated sample from the generator are. So you can think of it as a game theory. The two players, player one and player two, are playing a game with each other. So generator tries to fool the discriminator with fake samples x prime. So generator generates x prime, a lot of x primes, and you want those x primes to fool the referee, the discriminator. And the discriminator, on the other end, tries to discriminate between real sample x, the real ones, and the fake ones, x prime. So it's a referee. And they're playing a game against each other. Was there a question? VQVA에서 하나의 피처 맵이 하나의 코드로 매핑되는. 네, 맞습니다. 하나의 피처 맵이 하나의 코드로 매핑되기 때문에 이제 뭐 512개의 피처 맵이 있으면은 이미 레이턴 스페이스에 그럼 이제 512개의 코드 시퀀스가 생성되는 거고, 그 말은 이제 이미지가 더 이상 어떤 픽셀이 아니라 512짜리 코드의 그 배열로 이제 매핑이 이제 표현될 수 있다. 뭐 이제 그런 개념을 보시면 되겠습니다. 네. 그리고 이제 그 개념은 이미지뿐만 아니라 뭐 여기저기 다 쓸 수 있어요. 이제 뭐 오디오라든가 뭐 어떤 타임 시리즈 시그널이라든가 아무 데이터에나 다 그 개념은 적용될 수 있습니다. 일단 압축시켜 놓고 오토인코더를, 그다음에 압축된 스페이스를 이제 이산화시키는 과정이기 때문에 꼭 이미지만 써야 되는 건 아닙니다. Right, so it's a two-person game. So the overall structure looks like this. So generator gets a Z, which was sampled from a random noise. So generator tries to map the Z to a realistic samples as realistic sample as possible. And then the discriminator is on the top. Here's a discriminator. It sometimes see the real images, sometimes see the fake images. Actually, the discriminator should be seeing these two groups randomly. So sometimes fake, sometimes real, and then tries to distinguish between which is real and which is fake, right? So two different subgoals. So yeah, GAN so basically it's binary classification for GAN, because what discriminator does is binary classification. Given a image, given a sample, either fake, either real, given a sample, it's basically binary classification. Is it real or fake? So it's a 1 or a 0, 0 being fake or 1 being real, something like that. So two different subgoals. So for G, failing that binary classification is the goal. So what G wants is it wants to generate X primes, fake samples, that will fail, that will trick the discriminator, meaning that it will fail the binary classification. For D, discriminator, it wants to succeed the binary classification. So there's still the two-person game, the versus. Right, so if we remember the cross entropy, since we're playing a binary classification, so here, this is the binary classification, we resort to cross entropy. So please, hopefully, I hope that everybody is familiar with this formulation, cross entropy. So Y prime is the predicted value, Y is the true value, and then there's the positive, and then there's the negative term, the positive sample term and the negative sample term, right? So we take the positive samples and negative samples, and since we assume that half of our data consists of positive samples and half of the other half consists of negative samples, so we can rewrite the first. We can rewrite this formulation into this. So half, there's half, and there's half, right? Half. So separate positive samples and negative samples, assuming the same number of positives and negatives, and we put the 1 over half n and 1 over half n. So we take the half in front. So there we take the half in front, and then in the square bracket we have 1 over half n and 1 over half n, in order to make this in order to make the expectation form. So if you look at this part is sum over n half n samples, right? And this is also sum over half n samples normalized. So this can be seen as a expectation. So expectation over positive samples, expectation over negative samples, expectation over negative samples. So you can see that there's x here, and then there's x prime here. So you can see where this is going, right? So positive samples are coming from real images, and negative samples are coming from fake images. Which fake images? Fake images which are generated from the generator G, right? So that's where we're going with this formulation, right? So sample mean, but this is basically saying that sample mean is unbiased. So we have a sample mean here, and then we're changing that to an expectation because the sample mean is an unbiased estimator of population mean. You don't really need to worry about this, right? So we continue with this form, and then actually we just threw out this half term away. So because we're actually trying to optimize, so the constant terms don't really matter. So we just throw them away. And then we continue. So here, instead of saying positive and negative, we say real and fake, as I said. So positive versus negative, we convert it to real and fake, which is the game setting in our GAN model. And then, as I said, the fake distribution, the images from fake distribution, p fake is a fake distribution, right? Is actually coming from the random noise Z, right? So you can see it here. See here, we have a PZ, which is usually a uniform distribution or a Gaussian distribution. So some Gaussian distribution or uniform distribution. So some random noise, and from that random noise, we sample a Z. You can see the sample here, and then we put that Z into the generator. So that the generated sample would be X prime. So basically what's happened is you take X prime and then rewrite that as a GZ, which is generated sample. And then, right. So far so good. So, actually, I forgot to mention here, here. You can see that the Y hat has become D here. Because the Y hat is the predicted value, and the prediction in GAN is done by the discriminator. It's either fake or real, right? So the binary classification is done by the discriminator. So Y hat is now changed to replace with D here, right? So that's why we had D all the way so far, D, and then inside D there was DX prime, which is D, the discriminator, trying to classify X prime. We replace X prime with GZ. And that's why we are here. And finally, we are right here. We parameterize the functions D and G with actual neural network weights. So there's theta D and then there's theta G. So we assume that the functions D and G are parameterized neural network models. So it could be feed-forward networks or CNNs or RNNs or whatever, like transformers, whatever. So we arrive at this final form, right? So no questions so far, right? So pretty natural. We actually started with cross entropy, broken down into positive and negative side, and then we replaced it with actual distributions, the positive samples and negative samples, or in here, real fake samples and real samples. And then we replace the X prime with the generated output, and then we have the final form here. So this is actually the GAN objective. And we're done now. So the gist is all done. So as long as you understand this formulation, you understand GAN. And right. So we said that there are two different goals. So in here, there were two different sub-goals. For G, we want to fail the binary classification. For D, we want to succeed the binary classification. So since we have the GAN objective here, what G wants to do is fail this objective, and what D wants to do is win this objective, right? So that is why we have, for D, succeed the binary classification. So we want to maximize it. For G, we want to fail it, so we want to minimize it, right? So you can see the difference between the two. And also you can see the difference between the parameter that we're the parameter that's used as an argument. So we want to maximize this objective using theta d, which is the parameter of the discriminator. We want to fail or minimize this objective using the parameters of the generator. And you can see the first term here has nothing to do with theta g. It has nothing to do with the generator. It's basically just discriminator accepting samples from the real distribution. So it has nothing to do with generator. So we can just throw it away and we're left with this term only. So two objectives. Objective one is, so the first loss function, this is loss function 1, and this is loss function 2 for each of the discriminator and generator. Right, so again is a two-person so theoretically again is a two-person min-max game, because what D wants to do, discriminator wants to do, is maximizing, and what G wants to do is minimizing, right? So they're trying to they're basically they're like playing against each other, and they need to do it at the same time. They want, like, D needs to do its best, put its best effort into winning, and G needs to put its best effort in losing this objective, right? So that needs to be that needs to happen at the same time. They both need to learn and adapt at the same time, right? Yeah. So discriminator theta d wants to maximize, so that dx is close to 1 and dgz is close to 0. So dx meaning for real samples, we want this output to be close to 1. For fake samples, we want the output to be close to 0. For generator, we want the dgz, which is the fake sample going into discriminator. So we want dgz close to 1 on, so opposite, right? Opposite. For discriminator, we wanted dgz to be close to 0. Here, we want the dgz to be close to 1, and well, we don't have dx close to being 0, because dx has nothing to do with generator. Dx doesn't have any learnable parameter from G, right? So that's where this comes in. So dgz close to being 1, dgz close to being 1, and for dx close to being 1, and dgz close to being 0. So that's what we want, basically. So this is all theoretical, actually. So when D and G reaches naturally, because we're playing this whole GAN thing can be interpreted in terms of game theory. So there's naturally a Nash equilibrium. So when D and G reaches Nash equilibrium, then D's accuracy, the discriminator's accuracy would be 50%. It would be a random guess. So that means that the generator sample is so realistic, the discriminator is no longer able to distinguish between real samples and fake samples, because the fake samples are so realistic. So that's when D's accuracy, average accuracy, would be 50%. So that's when the two players, the D and G, have reached a Nash equilibrium. So conversely, what that means is that the GZ's distribution, so the output of the G, the generator, will be exactly the same as the real samples. So, I mean, this is what we want, basically. This is ideally, we want to train GAN model so that we see this happening. We see this Nash equilibrium happening, which doesn't really happen, actually, because in order for the game theory and the min-max game to work, both generator and the discriminator need to learn at the same time. But in reality, we train one model after the other. We alternate between training D, then training G, then training D, and training G. So which doesn't really guarantee Nash equilibrium. But anyway, so what this picture does is that at A, we're at the starting point. So the black dots are the true distribution. So this is PX, and the green line is the initial GZ, initial distribution of the generated outputs, and the blue dots here, it's decision boundary of the discriminator. So what needs to first happen is that we first train a discriminator. So we train D. then you can see that the discriminator, the decision boundary, has learned to adapt to the two distributions, px and gz, right? So you can see that up until here, up until around here, there's only a px support, only px is live, and gz is like, you know, it's almost zero here. Like gz is only alive like around this part. So up until this part, you can see that the discriminator has output of 1. And then as soon as gz becomes alive, so there's support of gz, and then also there's still support from the px, so there's like a crossing point around here, like this point is crossing point. So here the discriminator doesn't really have a good idea, so it is actually lowering its decision confidence to 0.5, and then after here, which is the end of the support of the px, px support, end of support, then all the rest is purely just fake, right? So that is why you can see that the confidence is now all 0 here, 0.5 here. So you can see that the discriminator's decision boundary has adapted from this wiggly line to this beautiful sigmoid line. And then since we've trained D, now it's time to train G. We train G. And now G, what G wants to do is it wants to trick the discriminator. It wants to fool the discriminator. So it needs to take a look at the decision boundary. And then what it does is that it slightly pushes this dump to the left side, so as to trick or fool the discriminator. So you can see now that the GZ, the distribution, has moved left side in order to fake or fool the decision boundary. And now in order to doing so, it is a bit closer to the true distribution of PX. So you do this again and again. You train D, you train G, you train D, you train G, DG, 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 you know, you go on until your GZ is exactly the same as PX, and your decision boundary is always lying at 0.5, meaning it's 50% random guess. 50% random guess. So that's what we want. We want the GAN model to ideally follow. So far, so good. So yeah, there's a bit of modification in actual GAN. Well, this is also back in 2014, 2015, but it's been a big deal back then. So the reason that I said that in reality we don't really follow the true game theory and the min-max game and all that in Nash equilibrium. One was that we alternate training D and G. We can't actually train both at the same time. So that already breaks the guarantee of Nash equilibrium. But another thing is that we actually don't play this. We don't play this game at all. We actually play a max-max game. So what that means is that in practice, G doesn't learn very well because G is trying to fool D. So that this was G's objective, right? So we want DGZ to be as close to 1, so that 1 minus 1 become, we try to go log 1 minus 1, which is basically minimizing this whole thing, right? So trying to fool D doesn't really work because in the initial phase, D easily overpowers G, right? Because it's so easy for D to discriminate between very bad image, which would probably be the output of GZ in the initial phase. It would be very low quality or like random image, right? So in the initial stage, D will have a very easy time overpowering G. So that means that DGZ will always almost be 0 because most of the time the output of GZ would be very terrible. It would be low quality. So DGZ would mostly be 0 all the time. So this, if you look at this part, this is the function, the plot of the log function of, well, actually you can see it here. We're missing the 1s. So this is the plot of log 1 minus DGZ, and the x-axis is DGZ. And you can see that in the initial phase, as I said, DGZ would always be 0, mostly 0 because discriminator is overpowering G. So that means that around here. So this is your initial phase. Initial phase, your loss function would play around this region, And unfortunately here, around this region, the gradient is usually 0. You can see that the gradient is very, very, very low. It's almost 0. Only when DGZ is close to 1 around here, then your gradient will try to look, start looking interesting, which should be the other way around. In the initial phase, your gradient should look interesting, and as you're coming towards the end of the training process, then your gradient should go to 0. But here, this is the other way around. At the initial phase, your gradient is almost 0, and only by going to the end, your gradient will be non-zero. So that's why G doesn't learn very well in the initial phase. So what we do instead is we actually play this game. So instead of playing this game, minimizing this, we play maximizing this. So it's the same thing, actually. It's the same thing. Instead of trying, so we still want DGZ to be too close to 1 in G's perspective, but instead of formalizing like this, we actually formalize this. So we're still trying to maximize DGZ in order to make it into 1, but it's maximizing, so there's no longer 1 minus this thing anymore. So if you look at this, this is the graph or the plot of minus log DGZ. And as I said, in the initial phase, DGZ would be close to 0. So we're going to play around here. And now the gradient looks interesting. That is why we play this game. So that means that we're no longer playing minimax game. We're playing max game, and the formulation is even different. So we're playing max game, so no Nash equilibrium. But the reality is that in practice, this formulation works way better than this formulation. So we play a max game, and it works pretty well. It works actually so much better than this formulation. So doesn't matter. Doesn't matter whether we reach Nash equilibrium or not, whether there's a guarantee of Nash equilibrium, doesn't really matter, because as long as our model generates good images, we're happy. All right, so we're moving on to training the GAN process. So we have double for loops. There's a for loop here, there's a for loop here. So it's a nested for loop. So the outer for loop is, going over different batches or different training iterations or whatever. But the inner loop, you can see the case steps here. So what's happening is for case steps, you update the discriminator. And for one step, you update the generator. So there's only, so it might seem weird because as I said, training generator is usually a bit more trickier. It's more difficult compared to training discriminator. So why is it that we train discriminator more number of times than this training generator? So that is because usually it's unless like, as long as the discriminator doesn't like completely overpower G, it's generally a good idea to have a very good discriminator overall. So we want the discriminator to be a good referee. We want the discriminator to have a good decision boundaries in order for the G to trick the D. So if the D is low, if the D discriminator is a low quality referee, low quality evaluator, then G wouldn't learn as well, because we need a good teacher to learn. So the student, which is G, needs a good teacher to learn. So that is why we want the discriminator to be a good teacher. So that is why we train a bit more number of steps than training the generator. But in reality, this is all this is all like different strategy. You can actually train generator more number of times than the discriminator, and it might still work. Actually, it all depends on your problem setting, your model architecture, and your training process. There's a lot of knobs. There are a lot of like knobs to tune, like knobs to twist, and a lot of different handles and levers. It's just training again is usually very, very like unstable. But basically, as I said, you alternate between training the discriminator and training generator, and then, one at a time. Discriminator, generator, discriminator, generator. All right, so far, so good. So yeah, what's the best value for K? Well, actually, there's no best value for K. You can start with 1, K equals 1, 2, 5, 10. It all depends on your problem. But actually, you should try a bunch of different combinations and then see which one gives you a seemingly the best image possible. All right, so when to stop training? So here, do we just have a number of training iterations for how many? Like, should we train for 1,000 steps or 100 steps or 1,000,000 steps? Like, how many steps should we train? Like, how many epochs should we run for? Because it's not like we have a validation set and then like we can evaluate our model from time to time in order to get the validation performance and then do an early stopping. It's not like we can do that here because we're training a generative model. So how do we stop? So there is no golden rule. Unfortunately, there is no golden rule of when is the best time to stop GAN training, because D and G basically oscillates. So because D and G are playing against each other, so they're like sometimes D will overpower, sometimes G will overpower. So it's like they're gonna go back and forth. And yeah, we never reach that. We theoretically Nash equilibrium is like a very appealing theoretical concept, but in reality, we probably never reach it because we use modified G loss. So typical way is you generate fake samples from time to time. So every 1 iteration or every 10 iterations or every 100 iterations, you generate a bunch of samples using the generator G, and then you look at it with your own eyes and see if you're satisfied. And if you're satisfied, then you're done. You terminate the training process. Yeah, if there's no visual improvement, you stop training. Or you can use something called evaluation metric, FID scores or inception scores. Like there are different ways to measure the quality of your synthetic fake samples. So we're going to talk about that today as well. So there are certain like proxy evaluation metrics for giving scores to how realistic your fake samples are. So if you reach a certain value of your FID score or inception score, then you can terminate as well. So this is the typical way. Or you can use some GAN variants, like advanced GAN, such as like Wasserstein GAN, which gives a more indicative G loss. Like, in GAN, original GAN, the G loss is not really indicated. It's not really helpful. So, but in Wasserstein GAN, the loss is a bit too, the objective function, the min-max objective function is a little bit modified so that your G loss is a bit more intuitive, is more instructional, is instructive, it's more like informative. So you can take a look at how G loss decreases, and then if you're satisfied, then you can stop terminating. But in original GAN, DNG oscillates, so there's no way of knowing when G is satisfying a certain criteria. Right. So if we've trained GAN, then how do we generate the fake samples? In VAE, what you did is you had an encoder, you had a Z, and then you had a decoder, and then you have fake sample X prime. So once you've trained your VAE, what you did is, hopefully, I hope that all of you guys participate in a practice session. What you do is, since you know that this Z follows a unique Gaussian isotropic Gaussian distribution, you take any sample Z prime from this Gaussian distribution, and then you plug that into decoder, and then you get an X prime, right? So that's what you did with VAE. GAN is very similar. You have a random distribution, you have a uniform distribution or Gaussian distribution. You take any Z from here, and then you put it through a generator, and then you have X prime, and that's it. So both for VAE and GAN, it's really easy to generate fake samples like as many times as you want, and it'll be really fast because you just sample one Z and then you put it through a decoder, which is usually, when you're generating images, it's usually CNN. So you put a Z into the decoder's CNN, and then you get a new fake samples, and you can do it many, many, many times. Right. So before we move on to the next topic, there's one final thing, which is really important concept, actually. There's something called mode collapse. So if you think of the game that the discriminator and the generator D and G play in the GAN setup, you can imagine there's a very easy way for G to cheat into winning the game, which is, what if G generates only one realistic fake sample? As long as G fools D with only one very realistic fake samples, then DGZ will always be one. Because GZ only generates one it's always the same image, always x, always like a dog image, or it's always a cat image, like just one very, very realistically looking sample, then G is basically winning the game. So that is like cheating the game, actually. So that's when we say the generator has fallen into a mode collapse, because it's only generate out of all the possible images, out of all the possible PX, it's only selecting one very specific sample, and this all Z is coming from a random distribution, right? All Z is just is going towards this. All Z is going towards this particular sample, this particular X sample here. So that's when we say that the GAN has fallen into mode collapse. So when G generates a sample of limited diversity, or maybe only one or very few number of different samples, this means that G is trapped in a bad local minimum. So we don't want that to happen. We want our G to generate as diverse images as possible, right? Realistic and diversity, those are the two important qualities of generative models, right? So how do we remedy this? How do we cope with mode collapse? One is easy, we tune the hyperparameter. Another is using GAN variance. So mode collapse has been a pretty, like a hot debate issue back in 2014, 15, 16. So back then, people came up with a bunch of different GANs to, GANs to handle mode collapse in a more, more sophisticated manner, more principled manner. So that's why they came up with Wasserstein GAN, on-roll GAN, a lot of different variants. These days, they don't use this. I don't think they use this as much, because now everybody's just resorting towards diffusion models. But mode collapse was a big issue back in 2014, 15, 16. Right, so moving on to VAE versus autoregressive versus GAN. Any questions so far? Any question? So this is basically the GAN objective function, the min-max game, and the modified max-max game, and mode collapse and all that. So I think this is enough to introduce you guys into GAN world. Any question? No. All right, moving on. So as I said, there are several different ways to generate images or samples, different families of generative models. So one is VAE, another is autoregressive models, pixel CNN as a representative case, and GAN. So these are differently generated samples. So you can see that VAE generates a very blurry image. As I said, VAE will have, for example, if your PX looks like this, then your Q would look like this, trying to cover, well, actually, it's too high. Your Q would look like this, trying to cover all the supports. So that is why it'll generate. And also the MSE objective function, the reconstruction objective function tends to generate blurry images. So that is why VAE generated images are not as like very, very crystal clear, like sharp images. They're like blurry. They're trying to capture all average at the same, like averaged images at the same time. You can kind of see like this image captures like a lot of different women at the same time. It's not like a one particular woman. It's like a multiple woman expectationed out, basically. Pixel CNN does a way better job than VAE in terms of image quality. So you can see that, it's pretty, you can imagine like this kind of people like living somewhere in the world, but there are still some artifacts, like, like here, you can see like this part is like a bit mushed out. Here, the ears are not super clear again here, but at least the facial structure is pretty well done. GAN has the has the sharpest images, like the features are very, very detailed. You can see even for autoregressive models, it's a bit smoothed out. It's a bit blurry. Like you can see, I mean, they look realistic, but still it's like it's kind of like, it's like there's like a lot of shadings in here, but you can see it in GANs, all like details of like the wrinkles and the eyebrows and your wrinkles here, like it's all very well captured. But the problem is that there's a lot of artifacts, and also the strands of hair. But in autoregressive model, there is no hair strand. It's just a bunch of hair lumps, right? So in terms of the detailedness of the image generated samples, GAN is doing the best possible job here, but none of them are perfect, actually. So there's like a pros and cons, right? And yeah, pixel CNN would take a very long time compared to GAN and VA in terms of inference time, because in pixel CNN, it's generating 1 pixel at a time. So VA, yeah, we talked about this. So sampling, we talked about the sampling procedure. Measuring the performance, it can be done by using the reconstruction loss between X and X prime. So, you can either use the likelihood, a posterior likelihood using QZ given X, or you can directly measure the reconstruction loss between X and X prime and measure the performance, like how good is my generator doing. And the image quality, vanilla VA generates very blurry image, and the modern VA generates better images. But then again, people don't use VAs very often these days. Pixel CNN generation takes a long time, slow generation process. But measuring the performance, you can calculate the likelihood directly using this factorized formula. You can just, as you sample your pixels one at a time, you can actually calculate exactly the likelihood of each sampled pixel, and then you multiply all of them, put a log in front of it, then you get log likelihood of your generated image. So it's that easy. Image quality better than vanilla VAE, but slow inference is the problem. Question from Ahmed, shouldn't the reverse scale used in VA select one mode from the original data distribution, which should result in a good? Yeah, that is a good question, actually. So that is why VA doesn't completely go like if this was PX, then if you only use likelihood, which is reconstruction loss, then it would only go you would get a very low quality estimation like this. But since there is a KL divergence to remedy that, it won't be as crazy as like this. It will be probably like this, like this, or something like this, basically. I'm not sure if we can guarantee that your QZ given X will exactly follow only one mode. I'm not sure if we can guarantee that, but you're right, Ahmed, because there's a KL divergence term. The learned distribution wouldn't look like this, at least. Good question. Hopefully that answers your question. Yeah, good. So we've talked about VAE, pixel CNN, and we're moving on to GAN. And GAN, the measuring performance is the problem. So I briefly mentioned something about FID score and inception score. We're going to talk about that right after this. So, but measuring performance is not easy. It's that you can take a look at the image with your own eyes. So that's one, but that's only qualitative. But usually we desire quantitative evaluation. Image quality, it has the sharpest image. If we are talking about style GAN, which is the most recent GAN variants, it can even generate very realistically looking 1K resolution image. So it's a very high quality. Before the advent of DALI 1 and DALI 2, the vector quantization models and diffusion models, GAN was probably, there was nothing that beat GAN actually in terms of image quality. So, but still, for GAN, mode collapsal arcs. So you need to have a very carefully handled data training process in order to avoid your model from falling into mode collapse. So cutting edge progress. So we talked about these three competitors, VA versus Pixel CNN GAN, but this was all way back in 2018, 2019-ish, 19-ish. But now we're living in a world 2022. It's usually diffusion versus autoregressive models. So this is the first image is coming from DALI 2, which is the first diffusion. I mean, in a chronological manner, DALI 2 came a little bit earlier than Imagine, which is Google's diffusion model. So DALI 2, you can see the quality of the image. You can see all the different small. So actually, this is a text to image. It's a conditional image generator. So the given text is this. So an astronaut riding a horse in a photorealistic style. So there is no image like this in the world. This is not a real image. And the model has never seen an image like this. So it has such a good, powerful compositional capability. It knows what astronaut is. It knows what a horse is. It knows what a photorealistic style is. It knows all the different ingredients. So you can compose them into a coherent picture like this. So you can see there's like a comet moving. There's like all the different bunch of different dots here, different dots depicting like the space, and then there's a astronaut with a proper backpack riding a horse, like such a high quality image. So this is diffusion, and another competitor you can say is the VQVA versus autoregressive model based on VQVA. So this is Google's party model, and the prompt given, the text given to this model is this: a map of the United States made out of sushi. It is on the next table next to a glass of red wine. So the text prompt is a little bit longer than diffusion model. That's what party claims, that is that party can take longer text prompts and then still generate very coherent, like well-aligned image. So you can be sure there's never in the history of humanity, nobody has drawn a map of the United States with sushis like this. So this is such a powerful ability of party model. It knows what a sushi is, it knows what a United States map looks like, and then it knows how to draw a United States map with sushis. And there's a proper red wine next to the map. So you can see how powerful modern text-to-image generators are. But unfortunately, you can see that the details are a little bit blurry here. I would say that's the downside of diffusion model. I mean, downside of the VQVA model, because diffusion models has a very, very high quality details. Like you can see the strands of the horsehair right here, but you can see you don't see all the different grains of rice. There's no grains of rice, just like mushed out. So the details are a bit blurrier compared to diffusion models. But all in all, way better than before, right? So after we've finished this semester, hopefully you won't be able to train this unless you have a lot of number of GPUs, but at least you know how it works, right? Right, so evaluation. A question from 이형근. VQ 방식을 generate test의 장점 무엇인가요? Because VQVA allows images to be converted to a sequence of codes or sequence of discrete codes, it has, I would say has better compatibility with text, because text is also a sequence of words, a discrete code. And if you can turn your image into a sequence of codes, then both are sequence of codes, and then you can dump them into a like gigantic transformer and then train it. So I think that it has a better fit. So that is why Party probably claims that compared to diffusion models, it can accept longer text prompts and then still generate very coherent image compared to how short the text prompts for diffusion model is. Because diffusion model employs a separate model called UNet. So UNet is a sequence of convnets that looks like an autoencoder. So in order for you to, so the architecture of diffusion model is that you have a separate transformer model that accepts text prompts and then generates a text embedding, and then you plug the text embedding into a UNet side by side. So it's not like there's one coherent giant architecture. There's UNet and transformer, but in Party there's only one thing. There's only one transformer. So maybe if you increase the size of the transformer, maybe VQVA will have a better image quality, but I don't know. We haven't gotten there yet. Right. So the evaluation. So evaluating GAN. GAN uses implicit. So there's something called implicit distribution, because in VAE and Pixel CNN we have explicit distribution function. In VAE we have Q z given x. In Pixel CNN we have the likelihood that looks like this. So we have explicit distribution, but in GAN we don't care about the distribution. We care about high quality images. So we say that GAN is using implicit distribution. The implicit distribution is actually embedded into the generated model. The generator G simply maps the random Z into a realistic sample. So the distribution is actually inside the G, the generator. So it's difficult to measure the quality of fake samples. So there are two popular metrics. One is inception score, IS, and there's another score called FID. And these days, inception score is no longer heavily relied on. It's usually FID score, and there's follow-ups like like precision and recall. Actually, precision and recall is usually used in information retrieval, but these days people use precision and recall even for generative models in images. But anyway, we're going to stick to IS and FID in this lecture. So inception score, you can, well, we haven't gotten to CNN yet, but inception is a name of a model developed by Google back in 2015, 16, 17, 18, because like there's inception version 1, version 2, version 3, version 4. I think version 4 is the end of it. So inception score uses a model called inception version 3, which is Google created model, Google created CNN-based model, and it's trying to classify an image into 1,000 classes. Basically, it's doing an ImageNet classification, basically. So in ImageNet, there are a bunch of different classes. Like there's bird, car, like dog, cat, truck, whatever. So there are 1,000 classes. And so this inception model is already a trained model. So it's a pre-trained inception v3 model. And what you do here is that since the inception model can have a 1,000 different softmax scores at the end, 1K, the 1K softmax, 1,000 dimensional softmax scores, we're going to use that to evaluate how great your image quality is. So what you do here is that two criteria. So what you want, given your image bunch of fake images, what you want to do is you want to measure in two criteria. One is image quality. So how does your individual image look like? Is it realistic enough? And another is diversity. So you have a bunch of fake samples, and you don't want your GAN to fall into mode collapse. So you want your bunch of fake samples to all point to different semantics, different objects. So you can calculate these two, the image quality and image diversity, using a inception model. So what you want is here, the image quality, a single image should have a focused PY given X. So if in terms of a single image, you put a single image into the inception version 3 model, you'll have a 1,000 dimensional softmax, and you want your softmax to be focused on one particular class as much as possible. If it's like, if you're like, there's like dog, there's like cat, there's truck, there's whatever, like bird or whatever. Like there's a bunch of different classes, basically 1,000 different classes. And if your softmax looks like this, then it means that your image is probably a very realistic dog, right? But if your distribution looks like this, like all even, very, very high entropy, that means that your image is very ambiguous. It's very confusing for the inception model to make a clear distinction. So that is why it will have a very high entropy. So that is why we calculate entropy of your output distribution, your softmax distribution. So if it's low entropy, if it's like if it's condensed into a single class, then you have a very high quality image. In terms of diversity, what you want is your marginal probability PY over all images should not focus on one class. So you don't want your image, if you have generated 1,000 fake images and it all goes to dog, 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 dog. That's not a good idea. So you want your fake images, bunch of fake images to be distributed all around the 1,000 classes. So you want your PY to be high entropy. So individually, you want your PY given X to be low, but overall, you want your PY to have high entropy. So that is where you calculate KL divergence between the two. So you want your PY given X to be low, and you want your PY to be high. So that is why you calculate the KL divergence between the two. So if your KL divergence is large, that means that your inception score is high. If your KL divergence is low, then it means your inception score is low. So you want your inception score to be high. Yeah, for a specific algorithm, I put a couple more slides after this, after the final slide today, so you can take a look at it. So this is basically the gist of inception score. FID score, inception score. So worst score can be 1, which means that this will give you 1. For example, if you have a 3-way classifier, so your inception, for example, let's assume that your inception model can classify images into 3 classes. And if your if your 3 fake samples, x1 prime, x2 prime, x3 prime, have a distribution like this, then your inception score will be 1, which is the worst score you can get. But if your inception score looks like this, like 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, then this is the best ideal case. And in that case, you will get inception score of 3, which is the same as the number of classes. Right. So inception score for ImageNet classes, then there are 1,000 classes. So you want your inception score to be 1,000. Right, moving on to FID score. So FID score is Frechet inception distance. So it is, again, using inception version 3. So it's a pre-trained inception version 3. And instead of using the softmax distribution, what you're doing is you're using the one that is right before the softmax. So this is the softmax. This is like 1,000 classes here. Right before the 1,000 classes, there's 48 dimensions. So there's basically 2,000 dimensional vector representation of your image. So your image would be 128 by 128 by 3 RGB, will be compressed all the way into this 2,000 dimensional vector. So using that, what you're doing is you're comparing distributions of real and fake. So you have a bunch of real images and you have a bunch of fake images, and you're trying to calculate the distance between 2 distributions. So you view image features as Gaussian. So you have bunch of real 2,000 dimensional vectors, a bunch of fake 2,000 dimensional vectors. So basically you put your real images into InceptionNet and get a bunch of 2,000 dimensional vectors, and you put your fake images into InceptionNet and get a bunch of 2,000 dimensional vectors. So you assume that each image feature as Gaussian distribution, and you calculate the distance between real and fake Gaussian distributions. And when you're calculating the distance, you're using something called Frechet distance. So that's it. So you have basically you are still using inception version 3, but instead of using softmax score, and in order to calculate FID score, you need a real sample as well. In inception score, you didn't require real sample. You just had to put your fake samples into your InceptionNet and then get the distribution of PY given X and PY, and that was it. But in calculating FID score, you need real and fake so that you can calculate the distribution distance between the two. So a bit more work is involved. So calculate feature-wise statistics. So this is the how you calculate the distance, Frechet distance between the 2 Gaussians. So there's mean covariance, and this is the following formulate equation for specific again. If you're interested in specific algorithm, you can resort to the final slide in this slide that I gave you. But the gist is that you assume that fake sample 2,000 dimensional vectors form a 1 Gaussian distribution, and real 2,000 dimensional vectors form another Gaussian distribution, and you want those 2 Gaussian distributions to be as closely possible as possible. That means that your fake samples are realistic. So that is what we want. So you want your distance to be as small as possible, which means that your images are realistic, your fake images are realistic. So you can see here, that what FID score does for you is that, for example, if you have a very low quality images like that, like, a lot of Gaussian noise, a lot of blurs, distortion, black and white, like salt and pepper, certain salt and pepper noise, as you increase the degree of noise, degree of this different types of noise, you can see the FID score increasing. So it is doing a pretty good job actually. So low FID score means realistic sample. So you can see that only the realistic samples give you near zero FID score. So 2 scores, IS inception score and FID score. You can remember them and then use them. All right, so finally, we're in the final section, application of GAN. Well, actually, GANs are no longer the hot topic these days. Everybody's using diffusion models, but still, like, there were very famous GAN extensions, such as text-to-image GAN. So this was proposed back in 2016 using a text prompt. GAN could generate realistic samples, but you can see that it is actually fallen into kind of a mode collapse. Like, they all look pretty similar. Well, this image not so much. So there's text to image GAN, and there's also cycle GAN. I mean, GAN was the hit for at least like very, very long, like at least 5 years or something in the deep learning world. Like cycle GAN was also like and then there's like star GAN. There's a lot of different domain adaptation GAN, style transfers, like transferring your deep fakes. They were all GAN based. So cycle GAN, you can, if you're already familiar, you'll know what's happening here. Like you're basically you're transferring styles basically. Like if you have a zebra, you can convert them into like regular horse, like brown horses. If you have a real photograph, you can style transfer to Monet style, Van Gogh style, Cézanne style. I'm not sure who this is. Ukiyo-e, I guess he or she is a Japanese painter. Anyway, you can like cycle GAN was also a big hit. And then probably the most recent state-of-the-art quality GAN was style GAN. Style GAN also has like version 2 and version 3, if I'm correct. So style GAN first proposed in 2019 and very high resolution sample. This is like actually this is 124 by 124, 1024. And there are a lot of various techniques involved with style GAN. There's putting your random Z into MLP before putting them into generator. And then there's adaptive instance normalization, which is evolved from batch norm. We're going to learn batch norm next week. There's bilinear upsampling, layer-wise. A lot of different techniques went into style GAN in order to make this beautiful picture. So, FYI, this is not a real person. This is like a fake person. There's no such person that looks like this in the world. I mean, there would be a person looking similar to like similar looking individual, but at least this is total fake. And you can see all the different strands of hair, the wrinkles around the eyes, the wrinkles around the mouths, the gums, the teeth, like everything is like almost picture perfect. And the knitting style of the head is all phenomenal. I'm not sure if diffusion or VQVA models has reached this amount of detail, is able to put this amount of detail into the image as of yet. Or maybe I'm mistaken, but usually if you look at like stable diffusion or Midjourney, like open source diffusion model, they're mostly like illustrated. Like they draw a very nice looking pictures and a lot of illustrations, but as far as like realism goes, I don't think they can generate this kind of detail as of yet, but probably they'll evolve. Right, so this is the end of the class today. So this Thursday, you're gonna train GAN from you're gonna implement GAN from scratch and then try to train it and then try to avoid mode collapse. I mean, some of you will probably, if you follow exactly as TA's instruction, you will avoid mode collapse. But if you play around a bit, you will quickly learn how easy it is to fall into mode collapse. And if you have time, you can play around with style GAN, different cycle GANs and star GANs and that kind of stuff. Right, and yeah, there are a couple more slides that are the inception algorithm and FID score algorithm. If you're interested, take a look at them. Any question before we end the class today? 네, 질문 있으실까요? All right, I'm gonna wait 5 more seconds before we end. Okay, no question. If you have one, please post them on Classroom. I'd like to make Classroom a very, very live platform for having discussions and questions, even among the students. So please do. All right, yeah. 뭔가요? 네, 2주 주어집니다. 네, 좋습니다. 그럼 오늘은 이 정도로 마무리하겠습니다. Thank you everyone, and I'll see you guys next week. 아니요, 아닙니다. 그 프로젝트는 그냥 페이셜 이미지 제너레이션이기 때문에 애플리케이션 계는 다루지 않습니다. 과제는 이제 저희가 아니 그 과제 관련해서는 저희가 따로 말씀을 드릴 테니까 지금부터 미리 걱정하실 필요 없습니다. 과제는 저희가 그 나중에 어나운스를 제대로 할 거예요. 네, 좋습니다. Alright, I'll see you guys next week. Bye bye.
감사합니다.
네, 감사합니다.